So which graphic do we want to use? So it all depends on what type of variable we're recording. And so how much time somebody spends answering emails, the amount of time someone spends is quantitative. So bar chart is only used for a categorical variable, so you can rule that one out. So if they were looking at whether they answered their emails or not, then we could use a bar chart. But since we're dealing with a quantitative variable, we can cross that one out. Scatter plot is if we're looking at two quantitative variables. Side-by-side box plots are used if you have one categorical variable and one quantitative one. And since we only have a single quantitative variable, though, we just use a single histogram. I was listening to a podcast and came up with this question because a large company calculated how much money they spend on employees answering emails, and they came up with about $30 million a year. So a lot of times kind of spent or wasted, whichever one you want to think of it, answering emails every day. So, anyone have any questions before we go to the next one? Okay. Great. I thought I added amount of sanitizer bought, so that may be a little confusing there. So if you put the square, that one was a little more nebulous, but the type of which airline you use is definitely categorical because it's going to, be Delta, American Airlines, one of those, assuming they survive the next few months. Well, those are the ones you could use. So airline is definitely a categorical variable because it's represented by a word. Good. So the red one up here is the interpretation of the intercept. So it's kind of our guess or a prediction for what y is when x is going to be equal to 0. Y hat is the actual predicted amount itself. A is the intercept. B would be the slope. And our slope is trying to measure how much we expect our response variable to change as our x variable increases by 1 unit of whatever we're measuring it in. So good job so far. Anyone have any questions before we move on to the next one? Okay. Great. I threw this one in there as a little bit of a foreshadowing to what we're going to be looking at when we start getting to inference, and that oftentimes we need a sample size of at least 30. But when you're doing linear regression, there isn't any sample size requirement. N is going to stand for normal. You want your residuals to kind of have a nice bell shape to them. So it's linear, no outliers, equal spread, and we want our residuals to be normal or symmetric and unimodal. So yeah, you want to remember to use the acronym LONE, linear, outliers, normal, equal spread. Any questions for that one? Okay. So how you can tell if a residual is going to be negative or positive, what a residual wants to do is it wants to measure the distance a dot is away from the line. So this red line's our predictions. It's going to be our y hat. The blue dot represents the actual amount or the observed amount y. And so the farther the dot is away from the line, the larger the residual is going to be. And we're usually just concerned about the size, the distance away it is, but you can also figure out if something is above or below the line based off the sign. If it's below the line, that means we over-predicted and the residual will end up being negative. If the residual is above the line, that means that if we take y, subtract y hat, it ends up being a positive difference. So any dots below the line will have a negative residual. Any dots above the line will have a positive residual. So I probably should have put what's the best way to describe the circle dot, maybe as the question. And how you can determine if something's influential is it's both a leverage point because it's far away from the middle, and it's a pretty large amount of carats, and it's a pretty large outlier. The circle is pretty far away from our fitted line. So something is both an outlier, has a large residual, and is either really far to the right of our scatter plot or really far to the left of our scatter plot. It usually ends up being an influential point. And if you notice, if you kind of ignore this dot and picture a line you draw through the rest of the dots, it's pretty different from the line that we have here. And that's kind of what it means to be influential, is it'll affect or change the way the line looks itself. Being a high leverage point or being an outlier on its own usually isn't enough to make something influential. But if you combine the two together, it'll usually drag either the line down in this case, or if the dot was up here, it'll pull up the line higher than probably what it should be. So any questions so far for that one? So leverage is, in class, we kind of thought of it as the seesaw. If a dot sits close to the pivot point or close to the middle of the seesaw, it's a low leverage point. It doesn't really, push that much on the line. So we kind of want to look for the middle of our scatter plot, kind of the average of x, and it looks like the average is probably around 0.25 carats, somewhere between 0.25 and 0.3. So the middle would be around here. And the farther a dot is to the left or to the right of the middle, the more leverage it has. And so leverage just means it can potentially move the line. It doesn't necessarily have to move the line. If this dot was up here, it fits really closely to the rest of the pattern of the dots, and so it wouldn't affect it. So something can be a leverage point, but not being influential. If this dot was more somewhere down here, it's really close to the middle, so while it's a large outlier, it doesn't really have the potential to move the line. It'd be like if you're sitting in the middle of the seesaw. No matter how big somebody is, if they're sitting really close to the middle, they're not really going to move the seesaw up or down that much. But if you take someone who's really large and move them to the end of the seesaw, so this is a large residual, move towards the end of the line, then it can have a big impact on the seesaw. Or in our case, it'll pull the line up or down. So in order to be an influential point, you need to be both an outlier and it needs to have high leverage. It needs to be towards the ends of the scatter plot and not toward the middle of it. Right, a point on the line could be a leverage point. So if this dot was right up here, it'd be a leverage point, but it doesn't necessarily have to be an influential point just because it's a leverage point. It could be, they have the potential to be, but they don't have to be. So you may want a calculator for this one. if you haven't gotten a calculator yet, now would be a good time. Forgot to mention that. You probably use the one on your computer. Did that turn it off for you guys? Okay, good. So how we go about using the line, technically there should be a little hat on this, but I couldn't figure out how to do it in Kahoots. But so the predicted temperature, if we do temp with a little hat on it, is equal to this equation where we have our chirps. So all we want to do is plug in the number of chirps we hear outside into here. We take 62, multiply it by a quarter, you get about 15 and a half. So we take 15 and a half, add it to 37.5. That gives us our magic number of 53. So anyone have any questions for this? Oh, so the hat, the actual temperature are those dots that we kind of saw on the scatter plot a couple of questions ago. And the line is going to be the predictions. And in statistics, our predictions aren't ever perfect. So we want to indicate there's a difference between the actual amount and what we're going to kind of predict or expect to see based off this line. So the actual temperature outside probably isn't exactly 53 degrees. It's probably a little bit different. So to indicate that our predictions are not exactly the same as what we observe, we kind of put a little hat, and just like we saw with p hat, hat means predicted. So this would be our predicted temperature. Good. So I kind of threw these in up here as a little bit of a trick because the slope you can't ever really use to determine how strong the relationship is. You can figure out that it's a decreasing relationship here because the slope's negative, or an increasing relationship here because the slope's positive. But the size of the slope you can change. The slope changes depending on if we're measuring something in depending on what the units are. So if we were measuring temperature in Fahrenheit versus Celsius, the slope would change. So you can't really determine how strong a relationship is between two variables by using the slope by itself. That's what correlation is. The farther the correlation is away from zero, the closer it is to either -1 or +1, the stronger the correlation. So the correlation of -0.08 is stronger than the correlation of +0.06. Any questions on that one? Okay. Great. So that's the whole purpose of random sampling is we want a sample that kind of matches the population that it comes from. And the best way to do that in statistics is we're just going to pick who we're going to include in our sample at random. And chance and fate tends to do a pretty good job at making the samples that we collect unbiased, somewhat reflective of the populations that we're pulling them from. So the triangle answer, what eliminates confounding variables, isn't random sampling, it's random assignment. So if we want to determine if our explanatory variable is what's causing the differences, I keep using smoking causes lung cancer, then you'd want to do an experiment to eliminate the influence of any other variables on kind of the relationship or associations that we're observing between the two variables we're actually studying. Sampling variability arises because we use random sampling. So if we didn't use random sampling, if we picked who we wanted out of the population, there wouldn't be any sampling variability. And how you reduce sampling variability, how you kind of get your samples to be more consistent with one another, is we'll just increase our sample size. If you take a random sample of 1,000 people, those samples that you get will be more consistently close to the population than the samples of 100 people would be. And then the whole purpose of doing a randomized experiment using random assignment is we want to try to create, we want the groups we're comparing at the beginning, the people who are going to smoke, the people who aren't going to smoke, we want to try to make them as similar as possible to one another. So that way, if there's a difference between them, it's because of whether they smoked or not. And that's kind of what random assignment does, is it makes the group similar to one another. Whereas what random sampling does, random sampling, again, kind of makes the sample you're looking at, or the sample you're collecting, similar to the population you actually want to learn about. So anyone have any questions about this one? Okay, on to the next one. So in order to claim that there's a cause and effect relationship between two variables, we need to conduct a randomized experiment. So we're not going to let the people decide what they're going to do. We're not going to let them smoke or not smoke. We're going to kind of remove any free will from the people we're studying and then randomly assign them to certain groups. And then only that way we'll eliminate those potential lurking variables or confounding variables, and that will allow us to claim cause and effect. So two variables can have a very strong association, but not be causally related. One of the examples we looked at was the amount of margarine people buy and the divorce rate in Maine have a correlation of 0.991. So it's a really, really strong association. But if you buy a lot of margarine, people in Maine probably aren't going to start getting divorced, or the other way around. So no matter how strong the association is, you can't determine cause and effect unless it was done via a randomized experiment. So any questions about that one? So the whole purpose of a random sample is that's when you pick people at random from the population. So you're still letting them choose what they're going to do. So if we're looking at smoking and lung cancer, we'll just go out, pick a random sample of people who smoke. We'll go out, pick a random sample of people who don't smoke, and then see who ends up developing lung cancer in 10 or 20 years. So because we're just picking people at random and not telling them what to do, the picking them at random will allow us to say, if smokers have a 9% higher chance of developing lung cancer in our sample, then it's probably around a 9% increased risk for smoking for the entire population. That smokers overall have a 9-ish% chance, higher percent chance of developing lung cancer than non-smokers do. But because we let them pick what they wanted to smoke or not, then we can't say it was the smoking that necessarily caused that 9% increase that we witnessed between the two groups. So if you want to generalize from a sample that you observe to a population, you need a random sample. If you want to determine that smoking is what caused the difference that we saw, you need a randomized experiment. And the problem that you have with people is you can't kidnap them off the street and force them to behave in a certain way. People still have free will. So usually when you're looking at studies with people, you have a choice. You can either take a random sample and generalize from the study that we conducted to the entire population, or you can determine cause and effect to where you get people voluntarily joining your experiment, and then you can, because they're volunteers, you can tell them what to do. And then you can determine cause and effect that way. So it depends on the goal of the study. Do you want to generalize the results back to everyone, or do you want to determine a cause and effect relationship? So there's two types of randomness. Random sampling allows you to generalize back to the population, and randomized assignments or randomized experiments allow you to claim cause and effect. So they're two mostly separate ideas, but when you're working with people, you usually get one or the other. You usually don't get both. So light bulb life expectancy is bell-shaped, so it's normal with a mean of 800 hours and a standard deviation of 50 hours. So which one of these would you want to use to try to figure out what proportion of light bulbs last longer than 750 hours? So for the most part, the rest of the numeric answers, I kind of worked out a formula for them, or I kind of given what you'd want to input into your calculator, so that way you don't actually need a calculator to do them necessarily. But what we end up having is the picture told us that the life expectancy of light bulbs are bell-shaped, so it'd look something like this, centered with a mean of 800 and a standard deviation of 50. So we kind of want to make a couple of tick marks, and each one of those tick marks will be 50 away from the previous one. Whoop. Is that better? Okay, so this tick mark would be 800, this one would be 850, and this tick mark would be 700. And then what you want to do is you just want to mark kind of where our particular light bulb falls. And so we want to know what percentage of light bulbs will last longer than 750 hours. So we'll just draw a line there. And then we want to know, do we want above 750 or below 750? They say last longer. So we want this area above. So if they give you the value of x, which we know to be 750, and you're looking for a proportion or a percentage, then the function you want to use in your calculator is normal CDF. So we'll go over, we're actually about to get to that. So the way normal CDF works is you want to put in your lower bound, your upper bound, the mean, and the standard deviation. So in our case, our lower bound is where we start shading at 750. Our upper bound, technically normals go on forever, so we just want to enter in some large number. We had a mean of 800 and a standard deviation of 50. So that's what we'd want to enter in to our calculator. So if we're given this area, if we know this is 80%, and you want to figure out how long a light bulb needs to last, so that way it's in the top 80% of all light bulbs, then if you're looking for x, if you don't know what this one is, then you want to use the inverse function. And the way the inverse function works is you put in the lower area, the mean, and the standard deviation. So if you bought a more fancy one, they'll give you an option of the lower area, the middle area, or the upper area. But if it doesn't ask you, it defaults to the lower area, which is what this part is. So if this part was, say, 80%, this would be 20%. So you'd want to put in 0.2 here, and that'll give you the x for that one. Any questions for that one? On the exam, you're going to actually have to input the number, but on the preview or on the review material, it'll kind of just give you the calculator inputs that you'll need. Good. So we want the top 20%. So what that's going to mean is now what we have is we have the same curve. We have 800 in the middle, and then what we want to look for is the top 20%. So top means we're looking at the right part of the curve. We kind of want to shade it to get that nice 20%-ish looking anyway. And then the question is, what's this value of x? So this is kind of switched from what we had in the previous one. Last time we actually gave you x, we knew that one to be 700, and we're looking for this area. Now we know this area is 20%, and we're looking for the x value. That means we want to use the other one. We want to use the inverse norm function. And what it wants is it wants the area below. So if there's 20% above, there's going to be 80% below. So we'll just put in 0.80 here, a mean of 800, and a standard deviation of 50. And that would give us how long a light bulb would need to last to be in the top 20% of all the light bulbs that this one particular company makes. So any questions about those two? Okay. So if you haven't yet, the formula sheet that you're going to be using, if you go to Blackboard, I'll give everybody a minute while we go over this. If you go to Blackboard, if you go to exam, and then at the very top, it gives the formula sheet that's going to be on the midterm. And so, especially since we're about to get into probability, you may want your formula sheet for that. And so it has the formula for a z-score. And all a z-score is going to measure is how far away a certain value is from the mean. And then we want to put them in terms of standard deviation. So what we'll do is we'll take the value we see, x, subtract out its mean, mu, and divide by its standard deviation, sigma. And so what we should be able to do kind of off the bat is the z-score will give you two things. It'll give you how far away. So the number tells you how many standard deviations away from the mean it is. And then the sign tells you if it's above or below average. If it's negative, that means it's below average. If it's positive, that means the x value is above average. 600 was below 800. So that kind of tells us we can at least rule out the positive ones. And so that just leaves us with negative 200, which is how many hours shorter it lasted. But in statistics, we kind of want to see how far away 600 and 800 are. So we take the difference, and then we divide by our standard deviation of 50. So negative 200 divided by 50 gives you negative 4. Yeah, the formula sheet's going to be at the very bottom of the exam because that's kind of where it let me put it. But it'll be included on the exam. And if you want to know how to use the functions on your calculator for the normal probabilities or the normal percentages, if you go to the midterm review, I answer some of those questions in the video, and you can kind of go step by step of how you use your calculator to get them. So I forgot to convert those to the actual raw numbers themselves. But how it's going to work is this actually kind of goes back to what we looked at in chapter 3. So what we're saying is we know that there are a total of 600 people that like Scandal, 400 people that like Empire, and 150 that like both. So what that's going to kind of look like if you kind of create a table for everything is we'll have likes, doesn't, Empire, likes, doesn't, So we know a total of 600 people like Scandal, which means if there's 1,000 people total, that means 400 people don't. And then it said there were 400 people who like Empire, which means that then 600 people don't like Empire. And then the last thing it tells us is that there are 150 people who like both. And then it says, if we know already somebody likes Scandal, so we know that they fall into these 600 people, kind of what's the probability they also like Empire? So we want to kind of find the people who like both, because your conditional probability, so the probability of liking Empire given Scandal, it's going to be the probability that they like both over the probability that they like Scandal. So the probability that somebody likes both is 150 over 1,000 divided by the probability somebody likes Scandal. There are 600 people out of 1,000. And that's going to kind of, if you reduce it down to, is going to be 150 over 600, or 1/4. And another way you can think about it is we know they already like Scandal, so we can just focus on this column. So there are a total of 150 people who like both out of the 600 people available, and that gives us our conditional probability over here of 150 over 600, or 1/4. So any questions about this one? So going back to it real quick is if you see the word given or if you see the word of, usually that's going to indicate that we're looking at a conditional probability. So it's given to us that they already like Scandal. So that means it's not random anymore. So you can kind of treat that then as your conditional probability. And so I just want to know, if we already know they like Scandal, what's the probability that they also already like Empire as well? So it'll be the 150 who like Scandal and Empire over the total 600 people who like Scandal. Yeah, P both is A and B. So both is going to be what we call a joint probability. It's the probability that they like both of them to start with. Oh, so if you want to access the formula sheet right now, if you go to Blackboard, exam, the very first thing will be set of instructions and the formula sheet as well. So 20% of homes watch Modern Family, 5% watch Duck Dynasty, and no one watches both. So watching Modern Family and watching Duck Dynasty then would be what? Sorry about the timers on this one. The first time I did this, I put way too much time, and I think this time I didn't put enough time. So I'm still trying to figure out the balancing on the timers. So if we look back, it says no one watches both. So if nobody watches both Modern Family and Duck Dynasty, and I use this as an example because it was a long time ago, it was about 5-ish years ago, but that's exactly what they found, was that no one who watched Modern Family also watched Duck Dynasty, and the other way around. In that case, those are what we call disjoint. The two don't really overlap. If you kind of think of it as a circle or as a Venn diagram, we have the people who watch Modern Family, and since nobody who watches Modern Family also watches Duck Dynasty, then the two circles don't overlap. Since the two circles don't overlap, they're not joined together, so they're what we just refer to then as disjoint. So what it means to be disjoint technically is the probability that someone watches Modern Family and watches Duck Dynasty. If they're disjoint, they can't both happen at the same time, so that's going to have a probability of 0. So you can't draw from a deck of cards, you can't draw both a black card and a heart, because there are 0 black hearts in the deck. So that's all it means to be disjoint, is the two can't happen at the same time. So no one in the survey liked both, so that means the two are disjoint. What it means to be independent is knowing one doesn't tell you anything about the other. Knowing the weather in San Diego doesn't tell you anything about the weather in Burlington. If we know it's raining in San Diego, doesn't really tell us if it's raining up here either. Independence just means that one event doesn't change the probability or affect the probability of the next one. So coin flips tend to be independent of one another. The first coin flip comes up heads, doesn't tell you that anything about whether the next coin flip is also going to be heads or going to be tails. So independent just means knowing what happens first doesn't tell you anything about what happens next. So how you can tell if something is disjoint, kind of our definition of it anyway, is, not disjoint. How you tell if something's independent how to tell if something's independent, that means the probability of A given B. Knowing what happens in B, knowing the first coin flip is a heads, doesn't tell us anything if the second coin flip is going to be a heads. So that conditional probability is just going to end up being the same as what it would be if we didn't know what happened with B. So if it didn't affect it at all, then the two are going to end up being independent of one another. An example I like to use in a deck of playing cards, the probability that you draw hearts is there are 13 hearts out of 52, or 1/4. The probability of drawing a heart, given the card is a king. So what we want to know is how many hearts are also kings, because we want the probability of a heart and a king. There's one king of hearts, and then we're going to just divide by how many kings there are. There are a total, that's not 1/2, that's 1/4. There are a total of 4 kings in the deck. So our probability, knowing the card is a king, doesn't change the probability that the card is a heart. So we had a 1/4 chance of drawing a heart to begin with. We have a 1/4 chance of drawing a heart if we already know that the card is a king. So these two are independent. Knowing one doesn't tell you anything. Knowing what type of card you draw doesn't tell you what suit of card that you have. So that's what it means to be independent. This kind of knowing what happens here doesn't tell you anything about the actual event or suit that you kind of actually want to know. So 80% of Americans live within an hour of their hometown, about 30% have a college degree, and 50% of college graduates live within an hour of their hometown. Good. So what a marginal probability is, a marginal probability is just the probability of a single event. It's the probability of A or the probability of B. If you're only looking at one event, then we're looking at marginal probabilities. If you're looking at the probability of A and B, we kind of mentioned already that we're joining these two together. So that would be a joint probability. And then the probability of B knowing that A happens or conditional on that A happens. This then would be a conditional probability. So if one event is no longer random, if we know the person has a college degree and we know what's the probability they live within an hour of their hometown, that would be a conditional probability because we already know they have a college degree. So it's not random anymore. The only random part is if they live close to home or not. So those are our 3 types of probabilities that we talk about in here. Marginal is only one event at a time, doesn't have anything to do with another event. Joint combines them together. And then conditional is just the probability of one event happening when the other event is no longer random, when we already know the outcome of the previous one. So it's going to be the same type of question with a different percentage this time. So this one says 50% of college graduates. So this kind of statement is what we looked way back in chapter 2, is that we already know then what's going to come after it. So 50% of college graduates. So we're only focusing on people who graduated from college. So that effect's no longer random. If you ever see this word of, whatever group comes after that is going to kind of be what we're conditioning on. So if we're just looking at college graduates, 50% of them live within an hour of their hometown. So since we know they're a college graduate, it's not random anymore. It's given to us, so it's a conditional probability. Where if it said 50% of people have a college degree and live within an hour of their hometown, that would be a joint probability. Generally, if you don't see the word and or both, something along those type of effects, that's going to be a joint probability. If you see the word of or conditional or if, so if someone's a college graduate, there's a 50% chance they live within an hour of their hometown. That would also be a conditional probability. So ofs, ifs, given, conditional indicate conditional probabilities. Both and together at the same time, those generally indicate whether we're dealing with joint probabilities. Any questions on that one? Okay. So same setup, but now you're actually going to be finding some probabilities for the next one. So if you put this first one, the way joint probabilities work, if we have the probability of A and B, what we can do is we can turn this into a multiplication sign, the probability of A times the probability of B, if A and B are independent. But if we look back, what it means to be independent is that if we know somebody has a college degree, that shouldn't change the probability that they live within an hour of their hometown. And it does. This is our conditional probability. This is the probability that someone lives close to their home if they have a college degree. And that's just different than the probability that anyone lives close to their hometown. So if someone has a college degree, it goes from 80%, drops down to 50%. So they're not independent. And how you handle non-independent events is we know the probability that someone has a college degree. That's 0.3. And then what we're going to do is we're going to multiply it by we want to take the probability that they live close to home, given that we know they have a college degree. And this one is going to be 0.5. So we can't just multiply it by the probability that someone lives close to home because they're not independent events anymore. If they were, you didn't have to worry about this conditional part, but because they're dependent events, you have to kind of update what happens next. So that's kind of what we're doing here. We know this person lives close to home. Now what's the probability? We know this person has a college degree. Now what's the probability that they also kind of live close to home? So we'll take the 0.3, the 30% of Americans that have a college degree, multiply it by the 50% of Americans with a college degree that also happen to live close to home, multiply those two together, and you get your 15%. And if you kind of think about it, what you're doing is if you want to pick both, you start off with your 30% of people that have a college degree, and you also want them to live close to home. Half of college graduates live close to home, so we'll take half of this 30%. We'll take 0.3, divide it by 2, or multiply it by 0.15, and that leaves us then with 15%. So any questions about that one? So whichever one, it's a good question. Whichever one you're conditioning on is the one that you need the marginal probability for. So if we knew that the probability that someone lives close, if we knew the probability that someone has a college degree, given they live close to their hometown, then what I would need to do is I would multiply that by the probability that they live close to their hometown. So it's whatever you're conditioning on, that kind of what goes out front, and then you're going to multiply it by the conditional probability of the other one. So in this case, they just give us the probability that they live close to home, given they have a college degree. So this is kind of the formula that we have to use up here, where if they told us what's the probability someone has a college degree, given they live close to home, this is the one that we'd want to use. So you want to make sure you know which conditional probability that you have, because the probability of A given B is usually going to be different than the probability of B given A. So you have to know which one you want to use, and then whichever one goes second, that's the one you're going to multiply its marginal probability. So we're looking at the probability of someone living close to home and has a college degree. So we know the probability of someone living close to home given they have a college degree. Since that's the one we're conditioning on, that's also the marginal probability that we're going to multiply by. So whichever one you're conditioning on, that's the marginal probability you multiply against it with. Okay, so the at least one part is kind of what people tend to get confused with all of them. So we know that if you just pick a person at random, an American at random, there's an 80% chance they live within an hour of their hometown. So if I want at least one of them to live close to the hometown, what that kind of means is if you see the words at least one, usually it's easier to find the probability of none. The probability of at least one is going to be equal to 1 minus the probability of none, because that's its complement. Because we could have one person live close to home, two people live close to home, three people who live close to home. So you'd have to find all three of those probabilities, add them together, and that's the probability of at least one. And those would take a really long time to do. So the easier thing to do is just find what you don't want. Just find the probability that none of them live close to home. And then since they're complements, they have to add up to the total. They have to add up to 100%. So if we know the probability of none, we can subtract it from 1, and that'll give us the probability of at least 1. So the probability that they don't live close to home, that's going to be 1 minus the probability that they do, close. So that'll give us 0.2. So if you just pick a person at random, there's a 20% chance they live more than an hour away from where they grew up. So now, if I want none of the three people to live within an hour away, that means I want the probability that the first one is far. And since we're picking them at random, that means they're independent. So we can just multiply the probability that the first one lives far away, the probability that the second person is far away, times the probability that the third person lives far away. So that's 0.2 times 0.2 times 0.2, which is 0.008. So if you pick three people at random, the probability that they're all far away from home is pretty small. So we want at least one. That's going to be 1 minus the probability that none of them are close, which we found to be 0.08 or 0.008, which will give us 0.992. So what you guys had, who put the yellow option, that's the probability that all three of them live close to home, because 80% chance the first person does times an 80% chance that the second person does times an 80% chance that the third person does. So if you pick three people at random, you have a little more than a 50% chance that they all live close to home. but we don't want all of them. We just want at least one of them. So there could be one person in this group that lives close to home, two people in this group that live close to home, or all three. So you're not finding everything you want. You're finding kind of one possible outcome that you would want, that all three of them, but there's other possibilities as well. So you're leaving some of the options out. So at least one kind of sounds similar to all, or that's kind of what people are tempted to do. But you want to remember, if you ever see the words at least one, find the probability of none of them. So you just change these 0.8s to the opposite, 0.2. Or if we were looking at college degrees, what's the probability that no one has a college degree, or at least one person has a college degree? Then 30% have a college degree, so that means 70% don't. So it'll be 0.7 times 0.7 times 0.7, subtract that from 1, and that'll give you the probability that at least one person does have a college degree. So anytime you see the word at least one, just find the probability of none, and then subtract it from 1, and it'll give you what you want. Some of the questions on the exam are going to be similar to the ones on here. I made the exam first, and then I made this. So some of these questions will be pretty similar. If you look at the kind of the practice midterm, there are 4 different question types. Those are the 4 different question types that'll be present on the exam as well. And that includes like a give me a number answer. So anything that requires words are going to be multiple choice or multiple answer. And then anything that requires a number is you give me the number. Okay, so how do we go about finding this one? So we kind of talked about if you see the word and, you want to change and into a multiplication sign. And it's easy if the two events are independent, but if they're not independent, you take the marginal times the conditional. If you're working with an or, you want to turn or into a plus sign. So we're going to take the probability that they live close to home or they have a college degree. So what we can do is we can turn this or into a plus sign. So it'll be the probability that they live close plus the probability that they have a college degree. The problem is if you just add those two together, that's 80% plus 30%, which gives you 110% or 1.1 probabilities. The cardinal rule has to be between 0 and 1. So that means we made a mistake. And what ends up happening, what you have to do is if the events aren't disjoint, if they overlap. So, if we want to find what's the probability that someone watches Modern Family or Duck Dynasty, we could just take the 20% plus the 5% and we get 25% because they don't overlap at all. However, in our case, they do overlap. So what we need to do is we want to subtract out the probability that they live close and they have a college degree, which we found this one earlier. So that's the probability that they have a college degree times the probability that they live close, given they have a degree. And so we found that to be 0.015. So we'll end up with 0.80 plus 0.30, subtracting out the part where they overlap. So 15% of Americans both live close to home and have a college degree. So we want to subtract out the overlapping part, which will give us the 0.95 that we're looking for. So 95% of people either live close to home or have a college degree. So any questions about that one? You just want to make sure that when you do an or, you always need to subtract out the overlapping part. You always want to subtract out the joint probability if the two aren't mutually exclusive, if they aren't disjoint. So the 0.15 is the probability that someone's close and goes to college. We found that up here. It's the probability that they're close to home and they have a college degree. So it's the probability that they live close to home, given we already know they have a college degree. They give us that probability of 50%. This was 0.5 times the probability that someone has a college degree. If you pick a person at random, the probability they have a college degree is 0.3. So we multiply those two together, and that'll give us the 0.15. And so in order to find a joint probability like this, I kind of have to give you one of three things. I have to give you a way of knowing that they're independent, because if they're independent, you can do what a lot of you guys just did and just multiply the two events together. So if having a college degree versus living far away, if those two were independent of one another, you can just multiply them together. However, if they're not independent, I either have to give you the conditional probability, which I gave you here. So 50% of college graduates, so conditional that they graduate from college, there's a 50% chance they live close to home, or I just give you the joint probability overall. If I just said that 15% have both a college degree and live close to home, that's kind of another way you can find your joint probability. So I either have to give you one of those three, that they're independent, I give you the joint probability, or I give you the conditional probability. If you have one of those three and the right marginal probabilities, you can find the conditionals and you can find the joint probabilities with only needing a marginal and one of the other. So we're looking at the GPA of engineering students at a certain college. Oh, no, that's a different question. We're looking at the population of states in the United States measured in millions of people. So how you figure out if there's an outlier? One, if you look at a histogram, well, there's one bar that's really far away from everyone else. That's usually kind of a dead giveaway that there's an outlier present. Another way of what you can do, if you want to be a little more, precise and a little less opinion about it, is you can find your interquartile range. You can take Q3, subtract Q1, which gives you about, what is that? 5.5. Increase 5.5 by 50%, add it to Q3. So say probably around 7.5. So it'll give us a cutoff of about 15 million. So any states with a population higher than 15 million would be considered an outlier. So basically these 4 states appear to be outliers. And then you do the same thing, is you take that 1.5 times your IQR, subtract it from Q1, and if you take 1.79, subtract 7.5, that gives you a negative population. States can't have negative population, so we know we don't have to worry about any low outliers. Another way you can check for outliers is you can make a box plot. If you create a box plot of these states' populations and you see a dot anywhere, if you see a dot on the right end on the high amounts, that indicates there'll be a high outlier. If you see a dot on the low ends towards the left of the box plot, that indicates that there's a low outlier. So there's kind of 2 ways about going it more objectively. You can either calculate differences yourself, or what you can do is you can make a box plot and check to see if there are any dots. But based off the histogram, it's pretty clear that there is a outlier on the high. So if you don't mind making sure that your mic's muted, otherwise I can get some feedback from you guys. Thank you. Okay, next question. Involving the same example, same histogram, same statistics about states' populations. So these negative, this is a subtraction, not necessarily a range. So how do we go about getting this for our answer? So because the histogram is right skewed, anytime you have a skewed distribution or skewed data, you don't want to use the mean and your standard deviation as your measures of center and your measures of spread because they're influenced by outliers and skewness, which means we'd want to use our median as our measure of center and our IQR as our measure of spread. So we take Q3, Q1, see how far apart the middle 50% or the middle 25 states are as far as population is concerned. So the state in the 25th percent has about 1.8 million people. The state in the top 75% is about 7.6 million people. If you subtract those two, that'll give you the range of the middle 50%. And when we're working with skewed data, we want to use our IQR. Whereas if we're dealing with bell-shaped data, we'd want to use the mean and the standard deviation. Also, kind of an aside, you can figure out, if I didn't give you this histogram, just from the statistics, you can actually figure out that the shape of the data has to be right skewed. It can't be symmetric. So how can you figure that out just from these statistics? So in order for something to be symmetric, what that means is what we would want to do is we'll start off at the middle, which I think we had a mean of 6.4. And then we kind of want to go up one tick mark and add the standard deviation. So 7.3 plus 6.4 would give you 13.7. We go up another tick mark, that give us about 21. And then we want to do the same thing down here. If we subtract one standard deviation, we end up with negative 1.3. Subtract another one, we end up with negative 9. So if the data were symmetric, it looks something about like that. The problem is, though, we're dealing with populations. Populations have a hard cutoff. There's essentially 0 people that live in Wyoming. So nothing can really fall below 0. So the only real part of the distribution then, of the shape that the data would take, would be up here. So if you just focus on the highlighted part, that would be a right skewed distribution. So if you notice that your standard deviation is kind of big, kind of close to what the mean is, in our case, it's even bigger than what the mean is, that's going to tell you usually then that the data have to be right skewed, especially if there's this hard cutoff at 0, that you can't end up with a state with a negative population. So any question about that one? Okay, moving on to the next one. So how do we determine this one? So if you notice, we're not given the median here. And the question asks about the majority, and majority means more than half. So your median is the halfway mark. You want to remember the mean isn't necessarily the 50% cutoff. That's the job of the median to do. And the way it works is if the data are right skewed, the mean is going to be dragged farther to the right than the median will be. So right skewed data means the mean is to the right of the median since it's affected by these high population states. So the median is going to be less than 6.4. So a majority of states then have a population less than 6.4 because what we have currently is our shape looks something like this. That's kind of the population shape, looks something like that. 6.4 falls somewhere here. And then our halfway mark, our median, we don't know where it is exactly, but we know since the data are right skewed, the median is going to be below the mean of 6.4. And so this is going to be 50%, and this is going to be 50%. So if we want, this whole area above, those two combine to make 50%. So if we want the total area here, then that'd be 50% plus something else. So a majority of states have a population less than 6.4 million people. Any questions about that one? Okay, on to the next one. So essentially, each state is losing exactly 500,000 people. So there's actually two right answers for this one. You can either put the standard deviation or the IQR. So this is kind of what we call a shifting. We're just going to take this entire histogram and move every state in this histogram to the left, since we're subtracting, by about 500,000. So all of these 5-number summaries down here, the median would shift down by 500,000, the min and the max would shift down by 500,000, Q1 and Q3 would shift down by 500,000, and the mean would also go down by 500,000, since we're subtracting half from every bar up here, from every state in these bars. But what's not going to change is how spread out these bars are. If these bars were suddenly more spread out, that would increase our spread, which is measured by the standard deviation or the IQR. And if you think about it, if Q1 decreases by 500,000, if Q3 decreases by 500,000, how far apart away these two numbers are didn't change. They both got smaller, but they got smaller by an equal amount. So they both shifted down by that amount. So your measures of spread, the standard deviation, and your IQRs aren't affected by just adding or subtracting the same number to everybody. But your measures of locations, your means, your medians, your mins, maxes, Q1s, and Q3s will be affected by shifting or scaling. You just add or subtract whatever number to your statistics, your measures of location, and you get your new means and your new medians and your new Q1s and Q3s. So what this blue bar represents is how much the mean is actually going to increase. So the state's population increased by 5%. So we're basically going to add each state's current population to it by that 5%. So we're essentially multiplying each state's population by 1.05. So if you're multiplying, that's kind of what we call scaling. What that's going to do is it affects all of your statistics. So every state up here, we're going to multiply its population by 1.05 to increase their population by 5%. So your mean is going to increase by 5%, or you can multiply it by 1.05. So 6.4 times 1.05 gives you that 6.7 million. And unlike shifting or scaling, adding or subtracting, your measures of spread are also influenced by this rescaling part. So the standard deviation will also increase by 5%. So we'll get 5% bigger. So we take 7.3, multiply it by 1.05 to give us our new standard deviation. If we calculate our IQR, so we take Q3 and subtract Q1, and we find our IQR for this one, the new IQR is going to be 5% bigger than our old one. So we'll take whatever the IQR is here, multiply it by 1.05, and that'll give us our new IQR. So when you're multiplying something, it's affected by everything. So every single statistic is affected by multiplication. So you just take your old statistics, multiply them by whatever you're multiplying all the individuals by, and you get your new ones. But only the locations. So means, medians, mins, max, Q1s, Q3s are impacted by shifting. So that adding or subtracting 500,000 wouldn't affect the standard deviation or the IQR. So we'll talk a little more about the test at the end. So it's increasing by 5%. So increasing means that it's growing, bigger. So that one's going to be, if we're multiplying it by 1.05 So it's increasing by 5%. So we're going to multiply 6.4 by 5%, get this 320,000. And then since it's increasing, that's how much we're adding to it. So we're going to take our old amount, 6.4, add this 320,000 to it to get the 6.74 million. Yeah, that's the last one. Okay, so how the exam is going to work is you'll need a webcam. I'm assuming if you have a laptop, probably has a webcam on it. And then what you'll want to do is if you go to exams, it kind of has instructions here. And if you click on here, it'll bring up the options for the quiz, the password, since we're using a Respondus lockdown browser to make sure to kind of increase the academic integrity of the test. It requires a password. The password will be given down here. So if you want to take the practice test, the kind of one to test to see if everything's working, if you click on this, it'll go through everything. And in order to get the Respondus lockdown browser, if you click on here, it'll give you a link to download it. And then once you download it, it'll have, there we go. And you'll want to, you actually have to take the exam through this. And that'll make sure that everything else on your computer is kind of not going to work. So you want to make sure to have an actual calculator with you in order to do the exam. So if you click on here, it works like a normal browser. You can go to the exam, you click on it, it'll open up. It'll check to see if you have a webcam going, and then you can get started with the exam. And then if you click on here, it'll hopefully go through all of that for you. And then there, again, there's the 4 different types of questions you'll see on here. You kind of want to check to make sure that you can see the 4 different types. And then one last thing is for the numeric ones, if you want partial credit, you kind of want to do what I did here, but you actually want to put the problem number along with it. So if problem number, say 10, dealt with a normal distribution, you kind of want to draw your normal curve out, put the number 10 next to it, and then sketch the area that you're looking for. And then you can either upload it as a PDF. If you upload it as a PDF, I can get feedback on it. If you upload it just as a picture, I can see your results, but I can't necessarily give feedback for what you may have gotten wrong or right. I'll still give you the partial credit, but can't necessarily give you why you got it wrong or right. Each question will have feedback if you get it wrong. So if you do get the question wrong after the exam's due date's over, you can go in, see which ones you got right and wrong, and then kind of how to get to the right answer itself. And I updated the exam to be 2.5 hours. And it's going to be on Friday if, since all this is relatively new, if something bad happens and a lot of people have trouble getting the exam to load up, then we'll have the exam on, we'll have a kind of like a redo for everything on Monday. So if you look at the practice exam, kind of the questions on here and the questions on the handout, that gives you the handouts that we've done in class, kind of gives you a good idea of the material that's going to be covered. If it's low enough, it'll be curved, yeah. And you can take it anytime on Friday. I'm going to be monitoring my emails basically in the morning up until 5 p.m. So if that happens, then if you have a problem, if you have some sort of issue, if you take the exam before 5 p.m., I'll probably try, to respond to you quickly. If you do it after 5 p.m., I may or may not get back to you all that quickly. And there are 37 questions on the exam. So you have to finish the exam in 2.5 hours, and you have to finish the exam before midnight on Friday. Otherwise, it kind of auto submits any work that you've done. So the word questions, so kind of similar to the ones on here, the word questions, are going to be multiple choice, the numeric ones. So like the ones with probabilities, you actually have to give me a number. And yeah, this is all East Coast time as far as when the exam will be made available at midnight on like midnight Friday morning. It'll be made available on the East Coast. And then it'll be due midnight Friday night on the East Coast. And so you want to have your own scrap paper available. There's not a way to actually work it out on Blackboard itself. So that's kind of why once you're done, there'll be a space you can submit your scrap paper below the actual exam itself. So you just want to kind of maybe take a picture with it. There's some picture to PDF converters out there that are free. There's a couple of links in the exam section on Blackboard. You can download those, convert the pictures into PDFs, and then you can upload them. As long as you upload your scratch work within about 24 hours after the exam, any mistakes you made on the numeric answers, you can get partial credit for, depending what you got right or wrong. So I'll be, answering emails. I'll have office hours tomorrow, probably, I'm thinking around the same time. And so if you have any questions, you can stop by office hours tomorrow, and it'll be kind of similar to this, but you can either chat in this way, or you can unmute your mic and you can actually talk. And you can either share your screen. I'll give you the ability to do that if you have questions in particular, or I can kind of work through scratch paper like here. Yeah, the webcam's designed so that way we know if anybody else is in the room, or if you have like a book or another laptop open. So that way it's kind of looking for any suspicious behavior. It flags something as suspicious, and then I kind of see snapshots of these suspicious behavior. If you want to see the cats, I'll be right back. If not, I'll post something. I'll post when the office hours are going to be held, and I'll go get my fat cat, who has really enjoyed me being here recently. So this is Tucker. He's pretty big. When he sits on my keyboard, he takes up the whole keyboard. But he's a pretty chill guy. His only one rules are don't pet the belly. Doesn't like being petted on the stomach. But other than that, he's a pretty chill cat. He just hangs out the whole time. But yeah, he's a pretty big boy. He's about 15 pounds, about a foot long, and he's pretty apathetic to a lot of stuff. But yeah, if you have any questions, email me, and I'll have office hours tomorrow at some point. And I'll be posting the video in Microsoft Teams, so you should be able to access it there.